My name's Josh Bongard, and I'm a professor in the computer science department at the University of Vermont, and I run the Morphology, Evolution, and Cognition Laboratory. Yeah, my definition of AI is any machine that can exert some sort of control over itself and its local environment. So what's very important to our approach to AI is what's known as embodied AI, a machine that has a body and is able to push against the world and observe and reason about how the world pushes back. So for us, a big part of intelligence is being able to not only survive in the world, but move through it and manipulate it in ways that are useful to self and to others. The guiding principle for my research on evolutionary computation is this idea of embodiment. So once we try and put AI in a machine, or it could be a biological machine if we're talking about organisms, the problems become very different and, in my perspective, very interesting. What shape should a machine or an organism have, and how should it use that shape to manipulate the world around itself? So that idea of embodiment, or the body, has really guided my intellectual interest in AI. So I've already mentioned this concept of embodiment, and as the name implies, it really means any agent that has a body, and that can be anything from a wheeled machine, if we're talking about autonomous cars, to a flying drone, to an industrial robot arm, or as we move into the future of robotics, some of these more state-of-the-art and future robots might have shapes that are very non-intuitive to us and don't really resemble anything we see in nature, which is a challenge, but also is an exciting opportunity, I think, for future AI research. So if we look at nature, brains and bodies have co-evolved. So unlike what you often see in AI and robotics, is a roboticist will often make a robot body, will make a robot. That body is then fixed, and then we'll apply some AI algorithm to try and improve the controller or the brain, if you like, for that robot. But of course, nature doesn't work that way. Over evolutionary time, if you look at the history of any species, there are usually changes in its morphology along with its nervous system. And that principle of trying to sculpt body and brain together using evolution is basically the common tool we use in my lab and others that work in the area of evolutionary robotics. So that's challenging. Evolutionary robotics is very much in its infancy. It's a very new tool, and so the evolutionary algorithms that we use to create robots, some of those evolved robots can't compete one-on-one with robots that have been built by hand by roboticists. But with the advent of 3D printing and big data and deep learning, we put all these technologies together. We're getting better at making more and more sophisticated robots. And these robots are viable, again, going back to this definition of being able to successfully manipulate the world around them, that they can continue to survive, to move objects or to do things, to move themselves, to help other people, if we're talking about robots in the home. They're able to manipulate their local environment to get the job done. They don't have to wait passively for data or information to come to them. They can reach out into the world and influence the world in ways that's beneficial to them and others. And that definition, I think, is what makes for a viable organism and for a viable robot as well. So a lot of the times when we evolve robots to move from one place to the other, or manipulate objects, or start to do the basic sensor motor things that human infants can do, as I mentioned, we usually evolve the body along with the brain. And what we often find is evolution comes up with solutions that are far simpler than we were expecting. So we do a lot of work in locomotion. That's very important if we're going to have machines that work alongside humans here in the real world. They need to be able to walk or somehow get from point A to point B. But often we get robots that don't have complex legs and arms like humans do. They roll, or they shuffle along. They come up with other, sometimes entertaining solutions. And they're entertaining because they're surprising. They often are able to do exactly what we ask those robots to do, but in a far simpler way than we were expecting. And that, I think, is promising for this approach, because again, often when humans are designing things, they tend to often overthink them or make them overly complicated. Evolution is not an optimizer, but a satisficer. It will give us, in our case, a robot that is just complex enough to do what we want it to do. So in our field, again, we face a lot of challenges in making good evolutionary algorithms that are able to improve body and brain together. And this turns out to be very challenging, and it's kind of intuitive for why it's challenging. If we're evolving a series of robots and one ancestor robot evolves the ability to walk on 2 legs, if it produces an offspring that has longer legs than the parent, then the controller or the brain is going to have to adapt for that robot. So any change that evolution makes to the body, the brain usually has to respond, and vice versa. So making these systems that can co-evolve and adapt to one another as the 2 subsystems of a robot are evolving can often be very challenging. And the bulk of the work in my lab is focused on improving evolutionary algorithms so they can sculpt body and brain successfully together. So as I was mentioning previously, we see these emerging technologies like 3D printers, which are making it easier for us to manufacture physical things. We're now just starting to see 3D printers that can print very simple robots. This was something that was just reported in the literature this year. So now that we can start to print these things, we can sort of automate the manufacture of robots. If we can couple a 3D printer with an evolutionary algorithm that can also automatically design robots, then we can start to design and manufacture lots of increasingly complex and diverse and hopefully useful or entertaining robots. So I think that's the future now, is the intellectual challenges of how to make these evolutionary algorithms work well for designing robots, and how to put all these technologies together so we can scale up this approach and produce lots of useful robots cost effectively and deploy them in lots of different domains. So it is definitely a common concern, this idea of the rise of the robots, and it's related to people's legitimate worries about AI. The technology, AI technology and robotics is improving so quickly. A lot of people have questions about where it's going in its entirety, and I think it's healthy for us to maybe not be fearful, but to really think carefully about where this technology is going. Personally, I'm very optimistic about it. Robots are not magic, they're yet another technology. Every technology, going all the way back to the hand axe, has had lots of positive applications and unfortunately a few negative applications. And it's not the hand axe's fault, it's society's responsibility to think about how to best put this technology into practice to make sure that it helps people rather than harms them. So there is definitely a lot of work to be done, not just within robotics and AI, but in the legal sphere, the cultural sphere, the social sphere, where we should all get together and really think about where we want to deploy these kinds of technologies.